This video is an introduction to our chapter on growth and mathematical modeling. In this chapter, we will investigate three main types of growth, those being linear growth, quadratic growth, and exponential growth. Given a scenario, once we identify the type of growth, we can use data and other assumptions from the scenario to create an equation that models growth, and then use those equations to make predictions. In the first two sections, we will review linear equations and investigate linear growth in models. For example, suppose you have a sales job where you earn $95 per day plus an additional commission of $30 per item sold. That $30 is our growth rate, and it is a constant growth rate in this case, meaning it stays the same no matter how many items you sell. That is what makes this a linear growth scenario. We can then use a linear equation like this, y equals 30x plus 95, to model the scenario and answer questions like, how many items must I sell in order to make $300 in a day? Or how much money would I earn for selling 10 items a day? Next, we'll investigate quadratic growth and models. Quadratic growth refers to a quantity that either decreases then increases or increases then decreases, kind of an up-down, down-up scenario. Our example here is, suppose you throw a rock straight up into the air at 150 feet per second. You can picture the rock traveling in an up-down sort of path. It rises into the air until it reaches its maximum height, and then it starts to fall back down towards the ground. We could model the scenario with this quadratic equation, y equals negative 16t squared plus 150t. We know this is a quadratic equation because the highest power of the variable t is 2, by the way. And we could use it to answer questions like, how high will the rock travel? Or how long until the rock falls back down to the ground? And in our last section, we'll investigate exponential growth in models. Exponential growth refers to a quantity that changes by the same percentage or factor for each unit of time. Consider this example where we invest $4,000 into an account, earning 3% interest compounded annually. In the first year, you will earn 3% of $4,000, and that amount will be added to the account. In the second year, you will earn 3% not just of the original $4,000, but also the 3% that you earned last year as well. This results in a sort of growth on top of previous growth, which is what we mean by compound or exponential growth. We could model this scenario with this equation, y equals 4,000 times 1.03 to the t power. And notice the variable t is in the exponent position, which is why we identify this as an exponential equation. This also makes the algebra a little more complex than what you might be used to, so we'll need to evoke some algebraic tools like radicals and logarithms. We could use this model to answer questions like, how much money will be in the account after 10 years, or how long until the value of the account reaches $12,000. A couple things to keep in mind are that mathematical models rarely give exact answers, rather they attempt to approximate the complex and messy world we live in. Models don't always account for every factor in reality. For example, when we mentioned throwing the rock into the air, we didn't account for things like wind resistance or the direction of the wind. Often we look at a stripped down or simplified scenario in order to create our models. A model is built using data and assumptions from the real world, and the accuracy of those inputs affect the accuracy and usefulness of the models that we create. But despite these criticisms, mathematical models are used in countless places of business and research, and they help to inform and develop our modern world. Thanks for watching.